All right, let's talk about it. Moment of inertia. Does that phrase just make you think of, I don't know, terrible physics classes and formulas that go on forever? Yeah, you're not alone. But what if I told you that for the ARE, it's not really about the math, it's about intuition? Today, we're going to demystify this thing and turn it into your absolute secret weapon for the PPD and PDD exams. So let's start with a really simple question. You've got two identical planks of wood. Same material, same size, same everything. You lay one flat across a couple of sawhorses and you stand on it. It's gonna sag, right? It feels super bouncy, might even snap. Now take that exact same plank, flip it up on its edge, and try standing on it. Whoa, it's like a rock. It's incredibly stiff. So what's the deal? Nothing changed about the wood, so what changed? The answer, my friend, is moment of inertia. You ready to crack this code? Okay, here's our roadmap. First, we'll nail down what moments of inertia actually is. Then, why it's a total game changer for your exams. We're going to uncover the one simple rule that explains everything, reveal its hidden superpower, dodge some common exam traps, and then wrap it all up with a killer cheat sheet. Let's do this. Okay, first things first. What even is moment of inertia? Honestly, forget the complicated name. From now on, I want you to just think of it as shape stiffness. That's it. It's a number that tells you how stiff a shape is just because of its shape. It has nothing to do with what it's made of. So here's the official breakdown. Moment of inertia, which we call I, is just a value, a number, and it tells us how good a cross-section's shape is at resisting bending. The bigger the I value, the less that thing is going to bend. It's that simple. And the key, as you'll see, is all about putting the area far away from the center. All right, so we know it's shape stiffness, but why is this so critical for the PDD exam? Well, it all boils down to one simple word: deflection. How much a beam sags. The ARE loves, and I mean loves, to test you on this, and moment of inertia is the master key to that whole puzzle. And this little relationship right here, this is your North Star. Don't worry about the full formula. Just get this part. It says that deflection, how much a beam bends, is proportional to 1 divided by E times I. That means if you want the deflection to go down, that number on the bottom, E times I, has to go up. E is the material stiffness, I is the shape stiffness. To stop the sag, we got to make E times I huge. And that gives us two powerful knobs to turn as designers. We can pick a stiffer material, right? Increase E by going from wood to steel, sure. But the real magic, and what the exam is obsessed with, is messing with the shape to boost I. Because using the same exact material but just arranging it in a smarter way, well, that's the whole game of efficient structural design. So this brings us to the core intuition, the big aha moment. It's this one simple physical rule that governs everything. I call it the farther is better rule. And it's not magic. It's just about putting your material where it's actually going to do some work. Now, to get this, we have to talk about something called the neutral axis. Picture a beam bending. The very top edge is getting squished together. That's compression. The very bottom edge is getting pulled apart. That's tension. But right in the dead center, there's this imaginary line that's not getting squished or pulled. It's experiencing zero stress. That's the neutral axis. It's kind of the calm eye of the storm. But this leads to an amazing insight. The material that's hanging out near that neutral axis, it's basically lazy. It's not doing much of anything. It's not in a lot of tension or compression, so it's not contributing much strength. The real heavy lifters, the heroes of the beam, are the fibers at the very top and the very bottom. They're doing all the work. So if all the material in the middle is lazy, what would a smart designer do? Get rid of it. And boom, you've basically just invented the I-beam. It's the physical proof of the farther is better rule. You take away the material from the lazy middle, that's the thin web, and you push it as far out as you can to the top and bottom flanges. And that's how you get an incredibly strong shape without using a ton of material. Okay, so the farther is better rule is the concept. Now we're going to talk about its superpower. And seriously, if you take one thing away from all of this for your life as a designer, this is it. It's the absolutely unbelievable impact of a beam's depth. Now, don't get scared by the formula. Just look at one tiny part of it. See how I equals base times height cubed divided by 12? The width, b, is just b, but the depth, h, is raised to the power of 3. That little 3 isn't just a number. It's everything. That is your secret weapon as a designer. And the result of that tiny little cubed term is just, It's mind-blowing. Look at this. If you make a beam twice as deep, it doesn't get twice as stiff. No, it gets 2 cubed, 8 times stiffer. Now, what if you triple the depth? It's not 3 times stiffer, it's 3 cubed, 27 times stiffer. That's an insane return on investment. A tiny bit more depth gives you a massive, massive jump in stiffness. All right, you've got it. You understand the core ideas. Now let's talk about how the exam is going to try and trick you, because they will. So let's make sure you're ready for their little games. The biggest trap by far is orientation. A beam doesn't have just one moment of inertia. Remember our wooden plank? When you stand it on its edge, you're bending it about its strong axis. The depth h is big, so the I is huge. But when you lay it flat, you're bending it about its weak axis. Now h is tiny and I is pathetic. The exam might show you a floor plan with joists laid flat and ask what's wrong. You'll know immediately. That's weak axis bending, and it's a huge red flag. Okay, here's trap number 2, and it's a sneaky one. The phrase moment of inertia actually refers to 2 totally different things. There's one for physics that has to do with spinning things. You can just forget that one exists. For us, for architects, for the ARE, we only care about area moment of inertia, the one that resists bending. So how do you spot the difference in a confusing exam question? Look at the units. If you see length to the 4th power, like inches to the 4th, that's our guy. That's the one you want. Oof, okay, we've covered a ton of ground. So let's boil it all down into one simple, powerful cheat sheet. This is the slide you might want to screenshot. This is everything you need to know. Here it is, the whole thing on one screen. Number 1, moment of inertia, or I, is just shape stiffness. Number 2, to fight deflection, you gotta make I bigger. 3, the golden rule is farther is better. Put your material far from the center. 4, the superpower is that depth is cubed. Doubling the depth gets you 8 times the stiffness. And finally, watch out for the traps. Always check the bending axis, strong versus weak, and only pay attention to area moment of inertia. Got it? This is your key. So I'll just leave you with this final thought. Moment of inertia. It's not just some random topic for an exam. It's a fundamental principle of design. It's written into the bones of every single building you've ever been in. So now that you really understand the incredible power of shape, how's that going to change the way you see the world around you? Go look. You'll never see buildings the same way again.